Lesson 6.2, Exponential Models. In this lesson, we'll look at our kind of template formula and alter it in ways to solve various types of problems. In some instances, an exponential function, such as y equals a times b to the x, needs to be altered to fit a certain situation. When we alter the equation, what we'll do is we'll kind of manipulate that b value, the growth or decay, and we'll manipulate the x value or the time. Let's take a look at the example on the right. It says in 2015, the population of a small town was 8,000. The population was increasing at a rate of 2.5% per year. Rewrite an exponential growth function to find the monthly growth rate. So now we need to alter what's going to happen with our rate in terms of the percentage and in terms of time. If we start off with our general formula, y equals a times b to the x, a would represent the original amount. That value is a constant. It won't change. A is 8,000. And b, remember the rule for growth rate, because this is increasing, we take 100% plus 2.5%. which would be 102.5%. And as we plug it into our formula, that would be 1.025. Our model then, without rewriting, would become y equals 8,000 times 1.025 to the x power. And what that would give us is the population increase every year. So here's where the change comes in. If we want to convert this formula and model the monthly growth rate, how many months are there in a year? There are 12. 12 is going to be used in our formula. So 12 months in 1 year. What we'll do with that is we're going to alter our x value first. I'm going to write y equals 8,000 times 1.025, and I'm going to write 1 times x, and the 1 represents the one time a year that percentage will increase. Then we'll take our 12, and I know this is going to seem kind of strange, and I'm going to rewrite 1 as an equivalent fraction, 12 over 12. This is our conversion to go from 1 year to a month. In a month, or 12 months is in 1 year. So we'll write it as 12 over 12x. We haven't changed the meaning of the equation. We're just starting to manipulate it a little bit to convert our form. Now, if we have 12 over 12 on the outside, what I want to know is each month, meaning there would be 12 in a year, I want to keep that 12 on the outside with x, that top 12. So now what we're going to do, and I know, we're going to rewrite that fraction once again, but I'm going to split it apart. The 12 in the denominator would be like 1/12 times 12x. There's my 12x for the number of months in a year. But now I want to evaluate that 1/12, and we can do that by raising 1.025 to the 1/12 power. And that would give us y equals 8,000. And now if you look at 1.025 to the 1/12 power, enter that into your calculator. We still get a decimal, but it's a bit smaller than our original one. It's approximately 1.00206. And then we can keep that 12x power. Again, what we did was we converted our exponential function in just its normal form to show a different type of growth rate within that year. So if the growth rate changes, we have to figure out how to convert the year into the new label. And in this case, it was months. And that would be our formula. So now we've got to figure out our growth rate, because that was ultimately the question. Rewrite the exponential function to the, there's two thes. I didn't even catch that before. Wow, you guys. We'll cross that the off. To find the monthly growth rate. So the monthly growth rate, if we do the 1% or the 1 minus that, or the 1, sorry, wow, the 1 plus the growth rate is that decimal after the 1. And in percentage form, that would be about 0.206%. What that means ultimately is each month, the population isn't growing significantly, but over the year, they get a 2.5% increase. You won't always ask to change the growth rate or to change it, but if you do, that would be the process to follow. With that change in formula, we can use our new model to predict the population in the year 2020. So the population formula started in 2015. Therefore, the year 2020 means X would equal 5. X represents 5 years. Now, what I'm going to do is actually plug this into both formulas to show that the prediction will work even though we changed from a yearly growth rate to a monthly one. Hang on. Oh my goodness, my cats just saw birds out the window and they lost their minds. Sorry, kind of scared me. Okay, getting back to the formula. Sorry, Y equals 8,000 times, whoops, 8,000. Well, that could be a big zero. We'll call that. 8,000 times 1.025. And if we enter that in for 5 years, our population is going to be approximately 9,051. I know there's a decimal after that, but we're not going to count a decimal of a person. So we're going to round this to the nearest whole person. And that would be about 9,051, the population in 5 years. Yes, I know, I am completely out of space. How great is that? So what we're going to do is take our new formula, and I'm just going to bring it over here so that I have enough space to write it. If we use that new formula with the same context of in 5 years, what is our population? We're just going to use this other option. Y equals 8,000 times 1. Oh goodness, I am going to run out of room here too. Hang on. All right, there we go. I got it to fit at least. Y equals 8,000 times our monthly growth rate, 1.00206, times 12x, or 12 times 5. And believe it or not, you guys, if you enter all of this into your calculator, you're going to get a slight decimal change, but the whole number is going to stay the same, 9,051 people. So the population matches up. And you may be thinking, okay, why would we have to do that if we had the other formula that worked the first time? Well, compound interest, if you put money into a bank, is where this kind of model is going to be beneficial. It says Tamira invests $5,000 in an account that pays 4% annual interest. So that's going to be kind of key for us. Annual interest. Whoa, sorry, hang on. I need a pen. Annual interest. So that means every year. That means our time is our normal A, B to the X formula. It says how much will there be for her in her account after 3 years if the interest is compounded at different times. So annually, semi-annually, quarterly, monthly, and daily. Compounding interest means instead of just having interest once a year, you can change up how many times the bank gives you money. Now that's not a super common thing, but it can be an incentive for what bank you'd want to go to. Over on the left-hand side, let's write out what's known as the compound interest formula. Looking at the formula, A equals P times parentheses, 1 plus R over N to the NT power. This formula is kind of the template that got us to our monthly growth rate in the population example up above. Here are some defining values for you. P is your original investment or your original amount. R is going to be your percentage rate. And T is time in years. What will change our exponent is if we want to get interest compounded more than once a year. So that would mean N would equal 1. When we change that up, that's what our N value will do to affect our formula. The N value is the compounding factor. For example, up above with the population, if we went from yearly to monthly, N would be 12. The A value, since it's on that left-hand side, is our output, which just represents our new amount over time. You'll definitely want a calculator for this. We're going to plug lots of things in to show that the more compounds you get in a year, the more money you get when you're done at the end. As we set the formula up, let's keep our constants in check. We know that Tamira is investing $5,000. That's the value for P. So P will equal 5,000. That won't change in this process. It's a 4% interest rate, so R isn't going to be 4, it's going to be the decimal equivalent of 4, 0.04. And then T for time is kind of like our X. Time is going to be, what do we say, 3 years. So T is going to stay at 3. It's when we change our value for N, the number of compounds in a year, that'll affect our formula. So let's get started. Annually, if you have something invested annually, that means N equals 1, once per year, which really doesn't alter our normal template for an exponential function. The formula would then be A equals 5,000 times 1 plus R over N, 0.04 over 1, to the N times T power, 1 times 3. So if we enter that in, 1 plus 0.04 divided by 1, that would just give us 5,000 times 1.04 to the third power. Entering that into your calculator, after 3 years, Tamira would have approximately $5,624.32. Not bad for putting money into a bank and then not doing anything else with it. Now let's watch what happens if we get our interest compounded semi-annually. That means semi-annual means twice a year, so N would equal 2. And here's how that affects our formula. A equals 5,000 times 1 plus 0.04, but now we have to divide that by 2. And then we do, instead of 1 times 3, we would do 2 times 3. And that would give us 5,000. 1 plus 0.04 divided by 2. Think about your order of operations. 0.04 divided by 2 would be 0.02 plus 1, 1.02. So if you notice, our parenthesis value got smaller. But here's the trade-off. Our exponent gets bigger. 2 times 3 is 6. And if you enter this into your calculator, we actually get a little bit more money. After 3 years, Tamira would have approximately 5,000, get a little money symbol in there, $630, and 81 cents. The next one, I'm going to set it up for you, but I really want you to plug it into your calculator to see if we can get a match. Quarterly. Think about, well, how many quarters are in a dollar? How many quarters are in a game? N would equal 4. That means throughout the year at 4 times, the bank would give you interest on your account. Our formula follows A equals 5,000 times 1 plus 0.04 divided by 4. That means our parenthesis again gets smaller, but then we're going to do 4 times 3. Therefore, our exponent will get bigger. See if you can simplify that parenthesis and determine our new amount after 3 years. Then press play and we'll move on. Whoa, I got a little aggressive. I wanted to make sure that we could have an efficient lesson in a fair amount of time, and I got away with myself. So, quarterly, you should have ended up with $5,634.13. As N increases, and once this video is complete, make sure to write down the monthly and daily just so that you have it for reference. As N keeps getting bigger and bigger, you get more money over time. That should seem to make sense. Now, eventually the goal would be to keep working beyond daily, and we'll get into a new kind of formula that we'll talk about in the rest of the video. All right, so make sure you have all these notes written out, and when you're done, Send me a picture.